Okay, hey. So at the end of the last video, we got to the point where we looked at an integral, like this, our usual friend, right? P dx plus q dy around the simple closed curve C. And we saw that, the general case that if Quix is not equal to pi, right, or pi is not equal to Quix, then in general, the integral around the simple closed curve is not going to be equal to zero. Okay. So one of the examples that we did was the following. Right. We said, all right, let us consider the integral around C of 2xy dx plus x dy. And that was going to take place over a triangular triangle of, going from the origin, okay, to the point 2, 0, and then to the point 0, 2, and then back home again, right? In a counterclockwise fashion around, the region, the enclosed region, which I referred to as a lake, right? So here's the lake again, right? And so, this is the region plus. All right, that's going to be very important when we take a look at Green's theorem, all right? So if you're driving around it, your left hand is pointing into the region. And I'm going to give this region a name, R. Okay? All right. And again, it's the region enclosed within this triangle. Let me do a little better here. And up here, yeah, 2, 0. And we have 0, 2 there. Okay? We parametrized this line integral because we didn't know what else to do with it because Quix was not equal to pi and we didn't get an automatic zero. So after parametrizing this, we got a value of, let's label this I, right? And I was equal to negative 2 over 3. All right. Okay. So, there is another theorem that lifts us from the drudgery of having to parametrize. And that theorem is called Green's theorem. This is what we've been building up to, right? We've had, one instance of path independence where Quix is equal to pi, and then we could use the fundamental theorem for line integrals, right? Remember that one, phi at the end point minus phi at the beginning point, where phi is the parent function. Well, now we have another nice little way of evaluating a line integral without parametrizing, and that's called, like I said, Green's theorem. Okay, so we're going to remember this value of I, okay, equals negative 2/3. And let's write down Green's theorem. So Green's theorem is the following. It says that suppose we have a line integral around the simple closed curve, right, like this one, like this triangle. Only I'll, make the lake a little bit, different, not a triangle. There, we have a lake, and we're going around that lake, all right, in a counterclockwise fashion, which means that, the lake itself is on the left-hand side if we're driving around, in a counterclockwise orientation, okay? And this is the curve C. So Green's theorem says that if we have the integral p dx plus q dy, right? Again, over this simple closed curve. And if p and q have continuous first order derivatives, we're not saying they're equal to each other, they just have continuous first order derivatives, then the integral, the line integral, can be given by Quix minus pi, dA, where A is the, the differential element with respect to area. And that double integral occurs over R. Okay, and we're going to do, partial proof of Green's theorem, but this is a fascinating thing. Now, there's other ways to interpret this, which is, really, really great. We can interpret this as circulation, which, I think I'm going to do later on in this video. But for now, we have, this crazy relationship, right? Okay, assuming Green's theorem is true, now, before I start, if Quix is equal to pi, right, then the line integral is 0, and of course, the double integral is 0, right, because double integral is 0, over this region is going to be 0, right? All right, so that's good. But like I said, in general, Quix is not going to be equal to pi, and we're going to get a non-trivial integrand. All right, well, let's apply this to the line integral that I just mentioned, the example that we did in the previous video. Okay, so let's see if that's going to be equal to the double integral of Quix minus pi over that triangular region. Cool. So, all right, so says Green's theorem, we have the line integral of 2xy dx plus x dy, right? It's a plus sign there. And here's the region, right? The region, as before, 0, 0 to 2, 0 to 0, 2, back home again, right? And so says Green's theorem, we take the double integral over this region R, okay, something very different, right, of Quix minus pi. Well, Quix is equal to 1, right? And pi is equal to 2x. So we have Quix minus pi is 1 minus 2x. And, that's using the differential area element, in rectangular coordinates, which is what we're going to do in this particular case. We have dA over here, but, given that this can be written as a type 1 region, I think I'm just going to change dA to dy dx. Okay, so we have the double integral of Quix 1 minus pi 2x over the region R. Okay. All right. Well, I said that this region R could be written as a type 1 region. And sure, because, if remember from before, if the tree is on the ground and this is up, here's the sun, right? And, this is down. So we can write this now, see, we no longer need, to know about this orientation because we're not going to compute the line integral, by, parametrizing it. We're just going to compute the line integral using Green's theorem. Now, I'm going to give you a little reason to believe it because we're going to hopefully get the same answer, but then I'll give you a little more reason to believe it. All right, so let's see what we got here, right? So this region now, right? No orientation, we just have a region. Well, this is y equals mx plus b, right? So y is equal to m, which is the y-intercept. Well, m is -1, right? Negative x plus 2, or 2 minus x. All right, so that's the y function. And then on the bottom, we have y equals 0, okay? And then we have x goes from 0 to 2, right? So we have 0 to 2 minus x, and then x goes from 0 to 2. And if we get a value of negative 2/3, we're going to be happy, right? Because when we parametrize this, we got negative 2/3. All right, well, as usual, folks, we're going to do the inside integral. And then once we do the inside integral, we'll pop back and do the outside integral. So on scrap paper, we have the inside integral, 0 to 2 minus x, right, of 1 minus 2x dy. So that integral is a partial integral with respect to y, all right? Good, 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 good. Okay. Well, that being the case, what do we have? We have y minus 2xy from 0 to 2 minus x. Cool beans? All right. So may as well factor out a y, right? So if I factor out a y, I have 1 minus 2x, and y again goes from 0 to 2 minus x, filling in the 2 minus x. Let's see what we have. we have 2 minus x times 1 minus 2x. And foiling all this stuff out, I have 2 minus 5x plus 2x squared. All righty? And that's the inside integral. So 2x squared, right, minus 5x plus 2. Fantastic. All right, so let's pop back up here. So here's the integral I, right? And now we just have the integral from zip to 2 of 2x squared minus 5x plus 2, okay? Dx, okay? So let's see what happens now. I'm going to erase this. I'll erase this. We don't need this anymore. Okay, so, if we get negative 2/3, we're having a good day, right? So 2/3 x cubed minus 5 halves x squared plus 2x from zip to 2. All right. So from 2, so we have 2 cubed, 8 times 2, 16/3. All right. Minus 2 squared, cancel a 2, minus 10 plus 4. So that's 16/3 minus 6, which is negative 18. Oh, I'm so happy. So 16/3 minus 18/3 is indeed negative 2/3. Wow. Wasn't that great? That's great. So that's a little reason to believe Green's theorem. So let me give you a little more reason to believe Green's theorem. So let's write down what Green's theorem is again, right? So Green's theorem says we have the integral around the simple closed curve of p dx plus q dy, right? And that's going to be equal to, if given, if P and Q have continuous first order derivatives. So I'll say P and Q are elements of C1, right? C1 means, continuous first order derivatives. So P and Q, belong to that family, right? So we have the double integral, and C is a simple closed curve, right? You see this notation. We've talked about that. So C is a simple closed curve. And, C encloses that, I said, all the relevant stuff before, right? C encloses, a domain here. Technically, C has to be inside of the entirety of C has to be inside of the domain within which P and Q have continuous first order derivatives. Everything we do today is going to satisfy that, so don't worry about it. All right, so Green's theorem says that this is Qx minus pi, the double integral of Qx minus pi dA, right? I'm going to actually prove it. The partial proof that I'll use is going to use a type 1 region for the part that I'm going to prove. All right, so here we're going to have the curve. The curve's not going to be like that. It's going to be slightly different. In fact, I'll but anyway, so the line integral of p dx plus q dy is equal to the double integral of Qx minus pi over the region enclosed by C. So here's R, the region enclosed by C. Okay, so here's what we're going to do, right? We're going to show. Here's the part that we're going to show that p dx, the integral around the simple closed curve that we are going to consider a type 1 is going to be equal to the double integral of negative pi dA, which is dy dx. All right. The corresponding part of that proof would be to show that q is equal to double integral of q sub x, over the region, right? But we're just going to show this part of p dx equals negative p sub y dy. All right. Okay. So like I said, it's a partial proof, but it gives you the spirit of what to do. And as I mentioned, there's other ways to think about this that will maybe have more physical significance, but I'm just hinting. All right, so cool. So let's take a look at this. Let's take a look at the double integral negative p sub y dy dx. And here's the region over which we're going to show that this this is true, right? All right, so here we have a type 1 region. Okay, I have an upper function and a lower function. I'll call the lower function g of x, all right? I'll call the upper function f of x. And then we're going to go from a to b, all right? Okay, well, now as far as the double integral is concerned, the double integral doesn't care about any orientation of these curves. I mean, yes, in terms of the theorem, but no in terms of the computation. So we're just going to do the double integral of that of that function. All right, so we can write this now as so y is going to go from the y coordinate is going to go from g of x to f of x, and the x coordinate is going to go from a to b. Okay. All right, delicioso. So let's look at the inside part of this. Okay. So the inside part, well, this is kind of nice, right? Because this is, we can evaluate this just using the fundamental theorem of calculus, right? So if I say, all right, well, we have the integral, this the inside, inner integral, right? Inner int, right, is g of x, integral from g of x to f of x of p sub y. Now I'll put in the arguments, p sub y of x and y dy, right? Well, that, can be evaluated just, by the old-fashioned fundamental theorem of calculus, right? I mean, the y integral of the y derivative just gives you the function p of x and y, right? No more p sub y, just p of x and y, where y travels between g of x and f of x. Thus, again, by the fundamental theorem, we have p of x f of x, right? So y gets the top value minus, again, as per the fundamental theorem, p of x g of x, okay? All right, let's pop back up to the integral that we have over here, right? So, all right, so, I'm going to need that again, but that's okay. Have plenty of chalk, right? So what do we obtain after doing that inner integral? Now we have negative a to b, all right, p of x f of x minus p of x g of x. All right, that was the inner integral dx. Well, we can distribute this minus sign, and now we get the integral from a to b, okay, p of x g of x, right, minus p of x f of x dx, right? Good. Okay, so that is going to be the double integral of negative p sub y dy dx, right? I mean, this integral, has, all the good stuff, the linear property. So, we could, just write this integral if we want. Is a double integral over r of q of x dA, maybe, and double integral of p sub y. Well, we chose, to do dA was dy dx, right? Again, over r. So, and the linearity on the left-hand side, we can do the same thing. So, if we have I'll write down what this is again so you can have it, right? So, we have the integral over c of p dx plus the integral over c of q dy, right? And, our plan is to show that this person is equal to that person, right? And we could go on to show the other, but the proof is similar. So, all right, so let's take stock of where we are so far. We've shown, so, I'll just call this the right-hand side, and I'll call this the left-hand side, okay? So the right-hand side, this is great. I have my new high-def cam. So the right-hand side, after distributing that negative sign, we have just, the plain old one-dimensional integral of p of x comma g of x, right? minus P of capital P of x, f of x, right, dx. That's what we had for the right-hand side. Okay, so now we're going to take a look at the left-hand side. So we're just going to take a look at this P dx, and this is, P of x and y, right, dx. And, this time orientation and, around the curve matters, right? So here's the curve, right? We said it's going to look like this. Can this be seen? Maybe I'll lower that a little bit. So, there we go. So here we have that, right? Type 1 region, A to B, G of X, F of X, all right? Uh, we're going to go around like this, all right? And we'll call the bottom curve C1. We'll call the curve on the right-hand side, which is just, constant. We'll call that C2. We'll call this C3, and we'll call this C4, all right? Looks like we're dissecting this whole thing. I guess we kind of are, right? And we have a lake on the inside. Just me up use my blue chalk again. Right, there we go. Okay. All right, so let's get busy with this. Well, we've spoken about the properties of a line integral and our ability to be able to, um, write the line integral, write a line integral consisting of several, curve segments, just as, the integral over each one of those curve segments and just add them all up, right? So all right, so let's look at the integral on C1, right? And then we'll sort of keep score someplace, right? So we have the integral on C1, no longer, no more circle, right? And then we just have P of x, y, dx, and that's going to be C1. Well, okay, we're back to parametrization, but this is not going to be too bad. So we can parameterize, instead of using t, I mean, we're used to t, that's fine. We can let x be equal to t, if you like. And why not? Let x be equal to t, and let's let y be equal to g of t, all right? Thus, dx is equal to dt. We just may as well have used x as a parameter, but, we're used to t, so that's fine. Now, dy is going to be equal to g prime of t dt, but you know what? We don't have to worry about dy because we only have, half of the integral, which is, for which the differential element is merely dx, right? So along C1, we just have the integral. Well, if x is equal to t, then t is going to go from, this is silly, I should have just used x, but whatever. T is going to go from a to b. So we have the integral from a to b of p of t, g of t, and because x is t, dt is dx, right? Well, t is just a dummy variable, no offense, t. And so we could just write this, with respect to x instead, all right? So, okay, yeah, so let's do that, right? I want to keep this drawing. So, all right, so far, what do we have for the left-hand side? For the left-hand side, we have the integral from a to b, okay, of p of x and g of x dx. Looking good so far, right? Yeah, good. All right. Let's take a look at parametrizing those vertical segments because, something nice is going to happen, right? So if we parametrize the vertical segments, this is a line segment. We can go through all you know, the bells and whistles. But if we were to parametrize this, right, we would have, x is going to go. Well, x is going to be stuck at b, right? So we're going to go from b to g of b, right? That's 1 point here, and then we're going to go from b to f of b, right? And we can create a line segment, between these two things. But when we do, if x is equal to b, for both of those things, then dx is going to be equal to 0. I mean, obviously dx is going to be 0, right? Because x is just going to be b. And if x is b, well, then dx is equal to 0 dt, which is 0. And because our integral, oops, so we have, yeah, so, right, I guess I should have put that. This is the integral along C1, right? And what I'm talking about right now is the integral along C2, right, of p dx, right? And because x is equal to b and dx is equal to 0, then the integral along C2 is 0. And for the exact same reasoning, the integral along C4 is 0. So the only thing we have to, see about, I'll just put C4 here. So C4 is 0 as well. The only thing left to do now is take a look at the integral along C3. Okay? And if the integral along C3 turns out to be negative x f of x, well, then we're in business. And you can pretty much see that it is, right? Because, if we have the integral, if we're going in this direction, we're gonna reverse the sign. But I want to do it. I want to do this formally, right? Because I think it'll be useful, right? So let's do the integral along C3. I'll erase all this other stuff because I'm starting to get a little bit of clutter here, right? So the integral along C3. Well, okay, now what happens along C3, right? Well, along C3, we have x is b, right? And then, the y coordinate, of course, is f of b. And then this point here is a comma f of a, right? Now, this is not going to be a line, so we can't parametrize it using, that little vector approach as we do. So what are we going to do? Well, okay, so here's what I'm going to do. I'm going to let x be equal to the following. b minus a t, okay? How do you like that? Where t goes from 0 to 1. Now, if t is equal to 0, note that we get x is equal to b, right? But if t is equal to 1, we have b minus b, no more b, minus a, and we have x is equal to a. Isn't that slick? Right? That's like that vector trick a little bit, because, x is going to be, some linear thing with respect to t. So, we're sort of doing, but we're not going to do it with y, right? Because y is going to simply be f of that stuff, b minus a of t, right? Yikes. All right, so along C3, what do we have? This is going to go to, right? So the integral of p dx along C3 is the integral from 0 to 1, okay? P of b minus a t, that's the x coordinate, right? And the y coordinate is f of b minus a t, okay? And then so this is p of x and y, right? Because, that p is, a component of some maybe force function or something like that, right? Okay, so right, so and then we have well, we have to find out what dx is, right? Well, dx, if x is given this, then dx is going to be equal to what do we get? Negative b minus a and then dt, right? Because the derivative x prime of t is negative, this is a constant, right? So negative b minus a, and then, then dt in differential form, right? All right, cool. So at the end of this, we have negative b minus a, right? Negative b minus a, and then dt, okay? Okay. All right. So what is all that about? Well, okay, this parameterization is good, right? Because as t goes from 0 to 1, right, we do traverse this function in the manner, that we want, with the orientation we want, right? Because x will start at b, and then as t increases from 0 to 1, x will make its way back down to n. All righty? So this is good. This is good parameterization. It works. But, it doesn't look so nice. So here's what we're going to do. It's a little bit crazy, but here's what we're going to do. We're going to go to u land, right? Why not? So we're going to let u be equal to b minus a t. Okay? All right. Well, doing so, then we have du is equal to minus b minus a dt. Happy news, right? So this piece here is du, isn't it? Right? This piece here is u, and this piece here is f of u. All right? Now, if we're going to go to U land, then we have to worry about making the numbers go to U numbers, unless we go back to T land, which we're not going to do. So let's write the T numbers as U numbers. So when T is 0, U is equal to B, right? So U of 0 equals B, right? And when T is 1, U of 1 is equal to A. All right, so let's put that there, and let's rewrite this integral. So we have now the integral from b to a, okay? P of u, f of u, du. All right? Now, assuming that this is an integrable function, which after we parameterize something, we hope that it is, okay? Otherwise, we wouldn't have a way to evaluate it. So we would be using the fundamental theorem to compute its value. Thus, we would have the antiderivative at A minus the antiderivative at B, right? But if we want to, change places with the A and the B, we can just say, well, the reverse, of the value using the fundamental theorem is going to be the negative of that. So we're going to get the negative of A to B, P of U, F of U, du, and once again, U is a dummy variable. No effects really. So we'll just rewrite it with x's, right? So we have A to B, and then we have P of x, F of x, dx, right? Oof. And that's the value along C3, which exactly corresponds to what we want, right? So we have negative the integral P of x, F of x, dx, right? From A to B, and then we could, the integral being linear, we can just, rewrite it and show that it equals to, it's equal to the top. Okay. So here's a nice line integral, which is going to, provide for us something interesting, and goes like this. So suppose we want to consider a line integral over, again, as we just described it. But here's the line integral I want to look at. I want to look at the line integral around a simple closed curve, and the integral I is equal to 1/2 the integral around C of the function negative y dx plus x dy. Okay. Well, according to Green's theorem, then, the 1/2 comes out front. We have the double integral over r of Qx minus pi. But look what Qx is, right? Q sub x is equal to 1. And look what P sub y is. P sub y is -1. So we have 1 minus a minus 1, right? And that's dA. So we have the double, let's see, we have 1/2, right? The double integral over the region R of 2 dA. Well, the 2's cancel, and we just get the double integral over the region R dA. Well, the double integral of 1 you will recall, over some region R is just the area, okay? The area of R, okay? So, this is kind of cool, right? If you do a line integral, around a simple closed curve and, record your movements, right? Your delta x's and your delta y's and your y coordinate and then, the negative y coordinate, your x coordinate, you can actually find the area of a lake by walking around it. We're going to consider 1/2 the integral of negative y dx plus x dy, right? Now, according to Green's theorem, we know that this integral is going to be the area of whatever is enclosed by C, right? So let's let C be an ellipse, right? So, using our familiar parametrization of the ellipse, okay, so let's say, I don't know, let's have an ellipse that looks like, all right, we'll make it general. So let's let our ellipse go from A to negative A, and then, from B down to negative B, right? And let's see what we get for the area of this beast, all right? Okay, so using, the parametrization, which we've discussed before for an ellipse, right? We have x is equal to A cosine t, and y is equal to b sine of t, and t goes from 0 to 2 pi, okay? Cool beans? Okay. All right, so, well, we need all the rest of the pieces, right? So we have, with x being a cosine t, we have dx is equal to negative a sine of t dt, right? And dy is equal to b times cosine of t dt, right? Right? And so let's put this, all together here. So we'll go to T land, we're parametrizing the integrals. It's going to be very, very easy, so you'll see soon, right? So let's see, what do we have? So we have the integral from 0 to 2 pi, and that's in T land. And we have negative y, so negative b sine t, right? And then dx, which is negative a sine t, right? Well, negative is positive, and we have ab sine squared t, all right? And, dt we'll put at the end. But look what we have for the next, part of the integral. We have x a cosine t and dy b cosine t. So once again, we have ab, but this time we have cosine squared t. Now we'll put the dt here, and I think everybody can see the magic, right? So we factor out an ab because they're constants after all, right? And then all we have left is the t integral from 0 to 2 pi of sine squared plus cosine squared, right, dt. And of course, that's 1. So we have ab over 2, the integral from 0 to 2 pi of 1 in t land, which is just t, right? So, well, we may as well do the whole thing. ab over 2, and then we have t from 0 to 2 pi, which of course is just 2 pi. The 2's cancel, we get pi ab, which is the known, area for an ellipse, okay? Neat, good stuff, huh? So, yeah, great. Okay, so the next thing we're going to do is we're going to compute the area of this cardioid-shaped thing using the result from Green's theorem that if we do this particular line integral, and I want to stress that, this particular line integral, it will give us the area of the enclosed region. It's kind of a miraculous thing. We don't have to establish that. We've already established that this line integral, 1/2 the integral around, the simple closed curve C of negative y dx plus x dy will give us the area. Okay, so we're going to do that line integral. But first, let's introduce this function because, you haven't seen it yet, right? This function is t. So, okay, x is going to be equal to sine of 2t, and y is equal to sine of t as t goes from zip to pi, right? So when t is 0, then we get sine of 0, sine of 0, so x and y are both equal to 0. Have a nice day. Now, when t is equal to pi over 4, right? 45 degrees, whatever. So 2 times pi over 4 is pi over 2. So the sine of pi over 2 is 1. That gives us an x-coordinate of 1 here. And you can see that occurs, roughly at 45 degrees. All right. And when yeah, so this is t is equal to pi over 4, all right? And, of course, when t is equal to pi over 4, the y value is going to be 1 over rad 2. Okay, so, progressing along, when t is equal to pi over 2, then let's see what happens. Well, 2 times pi over 2 is pi. Sine of pi is 0. So the x-coordinate is 0, all right, as shown. And then when, t is pi over 2, sine of pi over 2 is 1, so the y-coordinate is 1. So here we are up at 1. Now, as t passes pi over 2, and comes to 3 pi over 4, 135 degrees, well, the sine is the same in quadrant 2 as it is in quadrant 1. So 2 times 3 pi over 4 is equal to well, wait a second. Scratch that. Okay, so progressing along, when t is equal to 3 pi over 4, 135 degrees, then 2 times 3 pi over 4 is 3 pi over 2. And sine of 3 pi over 2 is negative 1. So this gives us the point, x equals negative 1. And then sine of 3 pi over 4 is 1 over rad 2, because the sine is the same in the second quadrant as it is in the first quadrant, right? When t is 3 pi over 4, this is not, this is, the beginning of the fourth quadrant, right? Because you get sine of 3 pi over 2, which is 270 degrees. All right, so all's good, right? So this point here occurs when t is equal to 3 pi over 4. Now, you don't need any, these specific values to do the problem. I just wanted, you to see that, this pair of equations, parametric equations, gives us, the object that we're looking at. All right. All right, cool. So now I've computed the differential elements, dx, because the derivative of the sine of stuff is cosine of stuff times the derivative of stuff, right? So we have cosine is 2t times 2. That's all good. And the derivative of sine is cosine. So we're pretty much good to go, right? Now all we have to do is evaluate this line integral. Like I said, when I introduced Green's theorem, sometimes you want to evaluate the line integral, sometimes you want to evaluate the double integral, right? Well, the double integral of Quix minus pi certainly is equal to 2 divided by 2 is 1, right? But if we were trying to describe this, as some sort of a maybe we could describe it as a polar region or something like that. But, the line integral is going to be easy enough to compute. So we may as well compute the line integral. We follow the path of least resistance. All right, let's go to work. So unfortunately, I have to erase this beautiful diagram, but you've all seen it. And you can replay it. Okay, so let's compute this line integral. So we're going to go to T-land because we're going to parametrize it. Let's see what happens when we go to T-land. Well, we get 1/2, right? The integral from 0 to pi, because that's what t is going to do. All right. And then we're going to put the values in here. So what do we get? We get negative sine of t. Okay. All right, that's fine because that's negative y. And dx is equal to 2 times cosine of 2t. All right, fair enough. And we'll put the dt at the end. All right. Oh yeah. So yeah, this needs a dt. Okay. All right. Then what do we have for the next part of it? Well, then we have x dy. Well, I've run out of room, so I'll do plus x is equal to sine of 2t, right? And dy is equal to cosine of t, and then we have dt, surrounding all of this stuff, okay? All right, perfect. So how do we do this integral here? Well, one thing we can do is use identities, trig identities, to take these cosine of 2t and sine of 2t and write them in terms of sine and cosine, and then maybe some nice things will happen. We'll see. All right, so recall that cosine of 2t, well, that has three identities, right? One of them is cosine squared minus sine squared. All right. So why don't we go with that one? Sine squared t minus sine squared of t. All right. There's others, right? Because we can write cosine of t as 2 cosine squared minus 1, or we can write it as 1 minus 2 sine squared. Maybe we ought to do that, and then we'll have everything in terms of sine and cosine. I don't know. Let's see. If we use 1 minus 2 times sine squared of t, uh, then we can make that substitution there. Let's go with that. We'll see what happens. And then, of course, sine of 2t, this is all scrap paper here, right? Sine of 2t, you may recall, is equal to 2 times sine of t cosine of t. If I give you a problem like this on the final, I'll give you the trig identity, so you don't have to memorize those, all right? So let's substitute all this stuff in here. We'll go with this value for cosine of 2t. All right, in the end, it doesn't matter, if you go down the wrong path, then maybe we'll have to try a different substitution. That's the way it is with integrals. That's why integrals are tough. Okay, so I'm going to make those substitutions right away. All right, so let's see what we get. So we get, I'm going to erase this stuff. We already have this. I need space. Okay, so let's see what we have. So this is the integral I. Well, actually, A. I'm going to call this A because we know that this is area. We have 1/2 0 to pi. All right, let's fill in everything that we know. Okay, so we're going to have negative sine of t, and then we'll have 2 times what we said we were going to use. What did we say we're going to use? We said we're going to use 1 minus 2 times sine squared of t. Okay, that's going to be the cosine 2t portion. Then for this portion here, we have 2 times sine of t, cosine of t times cosine of t, that's cosine squared of t. All right, and dt follows all this stuff here. All right. Okay, well, looks like we can factor out a 2 from everything, and then we can cancel that with the 1/2. So this goes, and this goes. All right, see, it's already looking better. All right, so let's distribute this sign here, and let's see what we get, okay? So what do we have? Well, we have the integral from 0 to pi, right? And to distribute the sign, so I have negative sine of t, and then we have plus 2 times sine cubed of t, because I'm distributing the sign, okay, and distributing the minus. Okay, so that's what we get so far here. Good. And then over here we have sine times cosine squared. Well, if we're going to write everything in terms of sine, at least that's, the way I'd like to try it, then we're going to use the substitution cosine squared is equal to 1 minus sine squared. That comes from the fact that cosine squared of t plus sine squared of t, okay, is equal to 1. So subtract cosine squared from both sides, and subtract sine squared from both sides, and you have cosine squared is 1 minus sine squared. So let's make that substitution. 1 minus sine squared, or dt. Looking good? Looking good. All right, so you know why I'm doing that. I'm thinking maybe we'll get some cancellation. It looks like we will get a little bit of cancellation, not a total cancel fest, but a little bit of cancellation. All right. So popping back up here, all right, we have that A integral 0 to pi. We have negative sine of t, negative sine of t plus 2 sine cubed of t, all right, plus sine of t. That's a happy thing, isn't it? And then minus sine cubed of t. Well, that's a happy-ish thing too. Happy-ish, right? So good. We have a little cancel fest. That's good. And 2 sine cubed minus sine cubed, well, that's equal to just plain old sine cubed. All right? T dt. Now we're on familiar ground. I know you know how to integrate this because we had to do it before on an exam, right? So remember, when we integrate an odd power of sine or cosine, we're happy because we can siphon off one of the signs for use as a du, right? Sine of t dt. I'm going to save that for a du. Why would I want that to be du? Because if I can write the rest of this in terms of cosine, and we can, right? Then we're going to let cosine be equal to u, right? Thinking ahead. And then du is going to be, roughly sine. I mean, minus sine, but we can deal with the minus sign. Okay, so let's see what we got. Yeah, so continuing, right? We have the integral from 0 to pi. Sine squared by the same, Pythagorean identity is 1 minus cosine squared of t, and then sine of t, dt, right? Cool. So u is equal to cosine of t, right? And that being the case, du is equal to negative sine of t, because the derivative of cosine is negative sine dt. And I'll just move that negative to the other side because what we have, saved for us, siphoned off is a sine, okay? Right? That sine of t dt, okay? All right, perfect. So, good. So where are we at now? Well, we have that a is equal to negative du replaces this stuff. So we have a negative sign, 0 to pi, and then we have 1 minus u squared du. Well, actually, we can't put 0 to pi in there because we're in u land. So we have to change the numbers to u numbers. But I'm going to go back to t land, and then we'll put the numbers in there. That's my usual outside. Okay, well now this is an easy integral in u land. The integral of 1 in u land is just u, and the integral of u squared is 1/3 u cubed between, somewheres, right? Okay, well, with u being equal to cosine, then we have that the value of the integral, oh, there's a negative sign out here, isn't there? Yay. So I distribute this negative sign. I have negative u plus 1/3. Cool. Cool. All right. So now going back to t land, we have negative cosine of t plus 1/3 cosine of t cubed between 0 and pi. You see, I can put those numbers back in because we're back in t land. All right, so when I put in a pi, what do we get? We get cosine of pi is -1, negative 1 is +1, all right? -1 cubed is -1, so we have -1/3. Okay, good. Now, using the fundamental theorem, we use parentheses to make sure that we, distribute the minus sign as needed. So we plug in a 0 and let's see, we get negative cosine of 0, so that's -1, right? This cosine of 0 is 1. We get -1 here, and then we have 1/3 here, so +1/3 there, okay? All right, good. Now let's see what happens when the smoke clears. The smoke clears. So we have 1 minus the -1, that's equal to 2. And then we have -1/3 and another -1/3, so -2/3. Well, that's 6/3 minus 2/3, and that gives us an area of 4/3. Okay, there we go. So the area of that nice little cardioid shape that we drew before is, well, I drew it better before, But anyway, the area of this thing is equal to, of this region R, is equal to 4/3. Okay? Cool? Cool. All right. So that's a nice application.